Everyone, come on in. I didn't want to wait till the last minute, so just playing. Anybody have any questions before we get all started and everything?
Hey,
Yeah.
Professor Younger.
Yes.
So I don't know, this is Logan. I don't know if you noticed, but I didn't take the test.
I actually was just getting ready to check that after class. So you didn't take it?
No, because so I was taking it from home and it asked for an access code and I didn't know what it was. I tried to email you, but
It didn't, yeah. All right.
emailed them.
If you're ready to take it, I can go ahead and I'll email you the code and so you can do it. I suspect Anissa might have had a similar problem, but I meant to take the code off.
Okay, so when did you want me
I
to
don't know if
take
Anissa
it?
took hers or not.
Well, so when did you want me to take the test then?
What I'll do is I'll open it back up and just give you, and will you be able to do it like tonight, tomorrow night, or Friday night or something?
Oh, I can definitely do it by tomorrow.
Okay, I'll just do
Yeah,
that.
I got it tomorrow. All right, thank
No
you.
problem. Sorry about that, Logan.
No, it's all good.
Actually, what I'll do is right now, I'm going to go ahead and take the password off of it because that should take care of it. So let me go over there real quick and do it. Anissa, did you have any problem taking yours? Or are you taking it tonight? I know I saw her log in, but I'm not sure she has her audio on or something. All right, let me check this real quick. There's Logan's test. Yeah, it doesn't say I had a code on it. I wonder. Let's see if it's this way.
I have a question about one of the questions on the test, but I think with her not taking the test, I'll ask after class.
Yeah, that could that'd be better. I appreciate that. I did find there was one particular problem with the test that I'm going to have to address, so it might even deal with that. But okay, it looks like maybe I think when I make the lockdown browser, sometimes that'll make take a password. Sometimes that'll make a password or retain the password that I erased. So that might be what's happening. I'm going to check it over here real quick while I still got people logging in because, like I said, it's okay. Now that I got people logging in, at least I can take care of everything. Still not there. Not there. There it is. Let's see. That's exactly what happened. It had a code left over from when I copied it from another place, and it left it in the lockdown settings when I erased it. So, all right, that should be working now, Logan, and I just got to change the dates so that you can do it. I see Anissa came back. Anissa, were you able to take your test?
No, I wasn't able to just because the webcam wasn't set up in settings for it.
Oh, okay. So nothing, no other problems in that though. That's cool.
No, there were no other problems. Thank you.
No problem. I'm going to check real quick because I saw that something happened with one of my other students, and the same thing could happen with you. So I'm checking with that just to make sure. It asked for an access code, and you shouldn't have had to put one in. So I'm checking with that. Ooh, got another student coming in. Settings. Yep, it did the same thing to you. So you would have been toast too. Yeah, all right, you're fixed. And now I just got to go in and change your dates for those, and everything should be good to go. Anybody else have any other questions? As we said, we do have 2 students that haven't taken the test yet. So it's probably best if you not ask any specific questions that are related to the test. At least not until those students take them. And I'm in the process of setting that up so they can do that ASAP. So now,
Speaking of that, I
yes.
I happened to miss the chapter 3 and 4 test.
Mm-hmm.
Can I take that after class?
The 3 and 4, that was test 2.
I don't recall the number. Yes, it was
Okay.
2.
Yeah, if it's 2, it shouldn't be too much of a problem. I'll see what I can do for you on that one. Tomorrow's
Okay.
28th. All right, I've got Logan, I do have your test set to the 28th now, so you should be able to do that. And I'm now doing the other ones. Remind me at the end of class to let me know, whoever that was just asking me about getting the test on 3 and 4. Remind me at the end of class so I can go back and set yours up. Otherwise, I'll be in a bit of a conundrum. So just wait at the end of class and remind me if you don't mind. All right, now I've got Logan's. Now I'm doing Anissa's. Anybody else have any other questions? Anissa, I'm going to do the same thing with you that I did with her. I assume that'll be okay. I'm making the due date tomorrow. And yeah, tomorrow. And that should take care of that. And then this will be that. Okay. I've got yours set up now too, Anissa, and it shouldn't have any passwords or anything like that that are needed.
Thank you.
You're welcome. Sorry about that, Logan, and hopefully Anissa won't have any problems. And thank you, Logan, for setting that up. All right, now what do? I can hide this. I can go there. Okay. So when we last talked, we were working on Newton's second law of motion. I had given you some very specific examples. I want to continue that, and I want to work some very specific examples so you'll have a idea of the full breadth of the type of things you should be able to do regarding friction and, of course, centripetal acceleration. So what I'm going to do first is share my screen. And here we go. Every time it looks like I need to reboot my own personal brain computer because I just get stopped in the middle of a sentence and can't say anything. Of course, it doesn't help that I'm looking at my image, and evidently I've got white hair and even a white beard, and sometimes I forget that. And oh, the trials and tribulations of getting older. Okay, so I've got that out of the way. That should be fine. All right, so first off, what I'm going to do is I want to solve a problem for you to help you understand the complexities that we face with regards to friction. So friction has this weird scenario in that one, static friction is always greater than kinetic friction, okay? That's, as I've mentioned before, that's the reason that we turn into a skid, or if you saw the movie Cars, you'll remember there was some cheesy part where the guy said, you got to turn right to go left. That is actually the same thing. They were talking about riding, in that case, on a gravel track as opposed to like a regular track. And with a gravel track, sort of the same thing happens. You go to take a left-hand turn and your back end swings out around to the right. And in order for you to maintain the direction you're going, you've got to turn your steering wheel to the right. So your back end shot out to the right-hand side and you turn your steering wheel towards the right-hand side. That's the same thing you're supposed to do when you're riding in the snow or ice. If you're going around, say, a left-hand turn and your back end starts to kick out to the right, you turn your wheel to the right as well. And what you're trying to do is get your wheels aligned parallel to the actual motion that the car is going, because now the motion is a little bit to the left because it was trying to make a turn, but it's also going straight ahead. But since the back end turned out like this, your wheels need to be put that way. So in doing so, if they're parallel to the motion, then you can recover static friction, which is the key part. So that's part of why that's the case. So we're going to look at a very specific example, and specifically what I'm talking about was static friction and kinetic friction. Yes, the static friction is larger than the kinetic friction, but the static friction also behaves a little separately, a little differently, because the kinetic friction is basically a set force that's going to be the static coefficient, or excuse me, the kinetic coefficient of friction times the normal force. Whereas the static friction force pretty much just does the bare minimum force that's required up to some maximum amount. At that maximum amount, though, if the force exceeds it, then basically it can't do any more. So hopefully this example will let you see that. So let's start off. I'm actually doing an example very much like one in your book. And what I'm going to do is I'm going to have a box with a coefficient of static friction, a coefficient of kinetic friction, and it's going to have various forces that I apply to it. And by doing that, I'm going to ask in each case, what is the friction force applied, and so on and so forth. So it looks like actually, I think that they might have actually pulled that example out of the 5th edition. So I'm doing something that was more like a 4th edition example. So yes, I guess I will just do that instead. So let me pull that up real quick so I can just refresh my memory. I don't want to like not have appropriate helpful numbers. So there it is right there. Okay, so what I'm going to do is I'm going to have a 10 kilogram mass. So to start off, I'm going to draw a level surface. And this level surface has a mass on it. The mass is 10.0 kilograms. And there's going to be a force applied to this. And that force is horizontal. And what we're going to do is we're going to, for part A, we're going to say if the force is equal to 0, what is the friction force? And part B, if the force is equal to 10 newtons, what is the friction force? Part C, if the force is equal to 20 newtons, what is the friction force? Part D, if the force is equal to 38 newtons, what is the friction force? And part E, if the force is equal to 40.0 newtons, what is the friction force? And I'll go one further and say what is the acceleration? Now, what I want to remind you guys is, or what I want to tell you guys is that mu static is equal to 0.40 and mu kinetic is equal to 0.30. Okay. Now, the equations we're going to use here, I'm going to write right here and say solution. And the equations we're using are obviously the summation of the forces. Actually, I shouldn't have written that that vector symbol over the sigma, but anyways, it's there. Let's see if I can erase it without too much harm. Good enough. Okay, so the summation of the forces is actually equal to mass times acceleration. That's one of the equations we're going to use. Another equation we're going to use is the static friction is less than or equal to mu static times the normal force, and then the kinetic friction is actually equal to mu kinetic times the normal force. So that's where we're going with this. We can, in fact, go ahead and figure out, what is the normal force, and then from that, what's the maximum static coefficient, or excuse me, static force, and so on. So let's do that now. I'll draw my free body diagram. I'll do a black coordinate system, say. I don't know what's going on, but evidently my dogs are raising heck. So that's X there. That's my Y-axis there. I'm going to have a mass here of 10.0 kilograms. Okay. The forces acting on it are, I'm going to use green for the positive direction, and I'll use red for the negative direction. So this force is a normal force. And then there's also a negative counterpart to that, and that force is actually M times G, which is equal to 98.0 newtons. Now, in addition to that, I have a force that we're applying, the F force, and I'm just going to draw it right here, and I'll use red, I'll use green because it's in the positive direction. So that's our F, and that varies from one part of the problem to another. And then what we're also going to see is that there is a friction force, and I'm not going to subscript it static or kinetic. I'm just going to use the script F to represent that it's going to try to oppose the relative motion between the bottom of the box and the surface that it's sitting on. So it's always going to be pointing to the left as long as we're trying to push the box to the right. So that's what we're going with. Now, I can take the summation of the forces in the y direction equals mass times acceleration in the y direction. In this case, we're actually going to imagine that the box is not bouncing up and down on the incline. It's not digging into the incline. And that's fairly normal when we're talking about things sliding across surfaces. The surface that it's sitting on perpendicular to that, there's going to be no motion. So I'm going to say the acceleration in the y direction is equal to 0. I'm going to let the student come in that just tried to come in. So with this, what I end up getting is that the normal force minus 98.0 newtons is equal to 0. So we've got that the normal force is equal to 98.0 newtons. And I'll call that equation 1. And we'll be able to use that quite frequently. Now that I have that, I can also say, let's call this equation 2. Oops. Let's call this equation 2. I can say that static friction is less than or equal to 0.40 times 98.0 newtons, which equals 39.2 newtons, if my memory serves me. Let me go ahead and pull out my calculator just to make sure. So 98 times 0.4 is 39.2. That's correct. And I'll also go ahead and do 3, which is the kinetic friction is equal to 0.30 times 98.0 newtons, and that should be 29.4. Again, let's check my math. 98 times 0.3, and that gives me 29.4, so I am correct there. So now that I have that, I'm going to go ahead and do my summation of forces in the x direction is equal to mass times acceleration in the x direction. Now, in these scenarios, I'm really not going to know what's going on as far as whether it's accelerating or not until I do the individual parts. So let's go ahead and start off with part A. With part A, I have F is equal to 0 newtons. So what I have is, dang it, I hate when it does that. What I have is F minus F is equal to, now in this case, there's no force applied, so I certainly can't overcome the friction, so it's not going to move. So I know the acceleration is 0. And this, in fact, tells me that 0 newtons minus F is equal to 0 newtons. And because of this, I say that the friction force is, in fact, would be a static friction, and it's going to be 0 newtons. So that's my first answer for part A. This will seem a little less trivial as we go along, hopefully. Got another student coming in now. And I have no idea, but anyways, my stupid thing keeps showing everything and being highlighted, and I don't want that at all. It's just aggravating me. Okay. So now I'm going to do part B, and part B, the force is going to be 10 newtons. You can see the 10 newtons is not big enough to overcome the friction force. So for part B, what I'm going to do is 10 newtons minus F. Since that's not big enough, again, we know the acceleration is going to be 0. So the 10.0 kilograms times 0 meters per second gives me 0 newtons. So from that, I can see that this does not exceed the static friction. And in fact, the friction that we're doing is going to be the static friction, but it's going to be exactly 10.0 newtons. And really what I'm showing you here is that the nature of the less than equal to symbol that's up there, I'll just put a blue asterisk by it, see where I just put that asterisk. The nature of that is that force is only going to be as big as it needs to be up until its max. And then when it gets to that maximum, it can't get any bigger. So now I'm going to go to part C, and part C is where the force is 20 newtons. So I'm going to say 20.0 newtons minus F is equal to, again, this is less than the 39.2 newtons. So I know the answer is going to be 0 newtons. But I also know that since it's less than the static friction, the friction force will in fact be static. And in this case, it's going to just make this equation true. So it'd be 20 newtons minus 20 newtons. So the friction force is 20.0 newtons for part C. Anybody have any questions on that? So hopefully that's pretty straightforward stuff. Let's go ahead and see part D now. Part D, the force is going to be, in fact, 38.0 newtons. Now, that's a lot bigger, and it's actually very close to the maximum static friction, but it's still less. And since it's less, that means the acceleration is going to be 0, and therefore the right-hand side is also going to be 0. And that means that the static friction is going to be the force that we're dealing with, and it's going to be 38.0 so that the equation is true. So again, I get 38.0 newtons, which happens to be exactly matching the force that we applied to it. Now things will get a little more dicey as we do part E. So part E, the friction force is actually 40.0 newtons, and then it's going to be minus F. And in this case, it does actually exceed the 39.2 newtons. And because it exceeds the 39.2 newtons, we know that it's going to actually accelerate. So on the right-hand side, I'm going to have to write 10.0 kilograms times A. Okay. Now, because of that, we're actually in a kinetic friction domain, and the kinetic friction is just a formula, mu k times the normal force, which we found was in fact 29.4 newtons. So this is going to be 40.0 newtons minus 29.4 newtons is equal to 10.0 kilograms times A. So I can say, for starters, the friction is in fact going to be the kinetic friction, and it's going to be 29.4 newtons. So that's the first part of the answer for part E. Now, the second part of the answer for part D is I've got to take 40 and subtract from it 29.4. And that gives me 10.6. So now I'm going to get, now I'm going to get 10.6 newtons equals 10.0 kilograms times A. So A is going to be 1.06 meters per second every second. And that's the acceleration. So anybody have any questions about that part? Everything seemed pretty reasonable to you guys? So like I said, this was sort of a pedantic question. It was just intended to teach you exactly what we mean when we say the static coefficient of friction is less than or equal to mu static times the normal force.
I got a question.
Yes.
On formula E, or
Mhm.
E, you have 10 kilograms times A, and underneath that looks like you have, is that 10.6 newtons?
Yes. When I did 40 minus 29.4, I got 10.6.
Okay.
No problem. All right, so let me show you another one. This one's kind of neat in that if it wasn't for friction, we would sort of be in a bit of a conundrum here, because what I'm going to do is imagine, or ask you to imagine, a scenario in which you're going to try to hold up an object by applying a force that's left and right, even though it's actually a vertical force that's the problem. So in other words, imagine a vertical force trying to move something, and you're only allowed to put a horizontal force on it. In general, you would think there's no way that can be done, because obviously forces, in order to cancel out a net force, you have to have a force that's anti-parallel to it. And you cannot have a horizontal force being anti-parallel to a vertical force. So that's sort of the setup of what we're doing here. So let me draw a wall. So what I have here is a wall. And what I am going to imagine is, yet again, a mass. So I'm going to put a box right here like this. And I'm going to say this box has a mass of, well, I'm going to say this box has a mass of 40.0 kilograms. Like that. Okay. I'm also going to say that the wall has a static coefficient of friction. Mu sub s is equal to 0.40. Okay. Now, what I'm going to do is attempt to hold this force up by extending my arm like so. And that's supposed to be my hand. Maybe I'll draw some crazy hairs on it. So that's my hand, which currently looks like a foot. And obviously I was in a bad car wreck and got my appendage mangled. But anyways, that's what the actual force is. So what I'm trying to do is I'm going to try to pin this box up against the wall. And I want to find what force I have to apply so that I can keep it from falling. So I'm really looking for F minimum. And what I mean by that is it's the smallest force I can apply in hopes of keeping it from falling downwards. So to do that, I'm going to, of course, create a free body diagram. But here's my solution. So first off, I'm going to draw a free body diagram. I'm going to use the black coordinate system because I can. Well, evidently I'm going to use a blue one. Must not have hit the dot properly. All right, what I'm going to do is I'm going to treat downward as the positive y direction, and I'm going to treat rightward as the positive x direction. And as long as you're just using two axes, there's no such thing as a wrong coordinate system. So don't worry about that. When we do 3 dimensions, everything has to be right-handed, which means if you held up your right hand like I'm doing here, your index finger should point in the direction of the x-axis, your middle finger points in the direction of the y-axis, and then your thumb points in the direction that the z-axis has to be. As long as you make sure your coordinate systems are right-handed in that sense, then you can't go wrong. But be advised, if you do make a left-handed coordinate system, cross products and stuff like that can be really problematic. All right, so here's my mass right here. That mass is 40.0 kilograms. Now the forces acting on it are going to be, I'm going to use red and green again for my positive and negatives. I have clearly a green force acting to the right. That force is the force that we're looking for. That's going to be F, which F is equal to question mark, for instance. Then there's going to be a red force that points this way, and that's the normal force. Now, there also is going to be a force in the downward direction, which is positive, of course. And that is M times G, which is the weight. And I think that's 392, but let me double check. 40 times 9.8 gives me 392. So that's 392 newtons in the downward direction. And what we're hoping for is that there can be a friction force this way, F, and it's going to be a static force. Okay, it's a static friction force because we're keeping it from moving. Everybody understand the problem now? Anybody have any questions about it or anything? Okay, so my solution is going to involve, of course, Newton's second law. So I'm going to do the summation of the forces in the y direction equals mass times acceleration in the y direction. And from that, you can see that I'm going to get 392 minus F static. And what we want is that to just be zero acceleration. So I'm going to put that A is approximately equal to 0. In other words, I'm trying to thread the needle and find the bare minimum of the F force that makes the F static big enough. So let's call this equation 1. Now I've got the summation forces in the X direction equals mass times acceleration in the X direction. This one's just going to be blatantly 0 because we definitely don't want it digging into the wall or bouncing off of the wall. In this case, we've got, in fact, a F force, which we're looking for, minus the normal force, F normal. Whoa. And that's equal to 0. So what that tells us is, in fact, that the normal force, Fn, is, in fact, going to be just plain F. So whatever force we apply, that's going to be the normal force, and that'll help us as well. So what I have to realize is that for F to be a minimum force to keep the box from falling, the static friction force must be a maximum. Now that means F static is going to be exactly equal to mu static times the normal force. So now I can plug that in to equation 1, and I'll see that 392 newtons minus 0.40 times, this time it's just going to be the actual F force. So I'm going to say 1 and 2, applied that, and that's all equal to 0. So from this, I can say that F is going to have to be 392 newtons divided by 0.40. And when you take that and divide it by 0.4, you get 980 newtons. So that's going to be the actual force that you're applying to it, but it's also going to be the force that is the normal force. So in fact, F minimum is equal to 980 newtons. Anybody have any questions on that one? All right. No questions? Okay. Oh, I see a chat going on here. Let's see what I missed. Okay, so I'm getting some questions about an access code. Got that. Mr. Short is a different person. That's probably the person that needs the test. I'll take care of that. All right. All right. So I've got one more friction problem that I want you guys to see worked. And here it is. What I'm going to do is I'm going to draw an inclined plane like such. This inclined plane has theta equal to 37 degrees. So in other words, this sort of looks like the 3, 4, 5 triangles, the main thing that we're doing here. What I'm going to have though is I'm going to have a box up here and its mass is 10.0 kilograms. Okay, and connected to that mass is a rope that runs parallel to the surface of the incline, and it's going to go over a pulley that's mounted to the end of the incline, and then hanging from that is a mass that we'll call just plain M. Okay, and what I want to know is for what range of M will the two masses stay stationary. So what I'm going to tell you is I'm going to use the same stuff again. Mu static is 0.40 and mu kinetic is 0.30. And that's part A that I just said here. And then part B, I'm going to say if M is also 10.0 kilograms, what will the acceleration be? Okay. Any questions on that? Does everybody understand what I'm talking about there? Okay, I was John, I think your mic's on because I keep hearing you grunting and stuff. Just thought I'd let you know. I think it was Mike or no, I said Mike, it's John. I don't know where Mike came from. All right. So here's our solution. So what's going to happen here is if M is below a certain amount, then the 10 kilogram block is going to slide down the incline. And if M's above a certain amount, then the 10 kilogram block is going to be forced to climb up it. So the first thing I'm going to do is try to attack sliding up the incline. So let's say what is the maximum? So looking for M max. In other words, what's the largest it can be and not cause this thing to accelerate up the incline. So that's what I'm going to do first. I will take a coordinate system that will be tilted, and it's going to be tilted like this and this. And in fact, this axis is going to be the positive x-axis, and this axis is going to be the positive y-axis. I'm going to put a mass right here of 10.0 kilograms. Now the forces acting on it, again, using red and green for positive, or excuse me, negative and positive respectively. I'm going to say there is a tension pulling up the incline, and that tension, of course, is going in the positive X direction. So I'm going to draw it with a green vector. Now that's supposed to be perfectly parallel to the X-axis. It's clearly not, but that's okay. All right. There's also going to be a normal force acting on the block. That'll be F sub n. There's also going to be a weight, which is M times G, or 98.0 newtons is that force there. Notice I left it blue because it's not aligned with any particular coordinate axes. Therefore, I shouldn't call it red or blue. Now, in this case, since I'm looking for M max, I can go on the assumption that the M is trying to pull the block up the incline. Therefore, the friction force is down the incline. So I can put the friction force right here as F. And since I'm looking for that maximum, really what I've got to do is use F static. So that will come in handy as well. Now, let me go ahead and work out something. You can see, for instance, that let's try this blue line here. Since that X is supposed to be the same angle as the inclined plane, that means this angle right here is theta, and that theta is 37 degrees. Now, if you look, this axis and this axis are 90 degrees, so this one would be 90 minus theta, and then this axis and this axis is 90 degrees again, so that means this one's got to be theta degrees. So that's how I'll work that out. That means I have a negative y component right here that is 98.0 newtons times the cosine of 37 degrees. I can do a calculation with that. 98 times cosine 37. That's going to give me 78.27. Notice that's 3 sig figs in the 98, but only 2 sig figs in the 37. So really these last two digits are not significant figures. There's also going to be a negative component parallel to the axis. And that one, of course, is going to be 98.0 newtons times the sine of 37. And this one should be like 58.24. So I'm going to say 98 times sine 37. And no, 58.97. That's what it was. Newtons. Again, we had 2 sig figs on the angle, so only the 58 is significant. But again, you always want to carry extra sig figs in the intermediate calculations. That way you're not rounding multiple times. So now I'm in a position where I can do my summation of the forces in the X direction, summation of forces in the Y direction. I'm going to go ahead and do that now. The summation of the forces in the Y direction is equal to mass times acceleration in the Y direction. Again, we're assuming it's not doing anything crazy, so that acceleration is going to be 0. And this gives me, in fact, that Fn minus 78.27 newtons is equal to 0. So equation 1 is that the normal force is equal to 78.27 newtons, where only the 7 and the 8 are sig figs. Now I can do the summation of the forces in the X direction is equal to mass times acceleration in the X direction. In this case, I want it to work out so that it's just barely 0. So I'm going to say A sub X is approximately 0. And then that way we can capture the bare minimum, if you will, force that the lower, or the bare minimum mass that M can be. Obviously, I got a second free body diagram I got to draw for that, but let's go ahead and start here. What I'm going to get is T minus the static friction force minus 58.97 newtons. And all of that should add up to give you 0. I'm going to call that equation 2. And now I'm going to draw a free body diagram for the hanging mass. And in doing so, notice I have decided to make the 10 kilogram mass going up the incline is the positive direction. So I got to make, I should make the axes for the mass M consistent with that. So what I'm going to do is I'm going to assume that the x-axis for the mass M points downward. So here's my free body diagram for the mass M. And what I get here is this is the positive x direction. The mass that I have is M, and the force that's acting goes, of course, in the positive direction. So I'm going to say this is just a force M times G. And of course, what's impeding that acceleration is the tension T. So I can take, again, using the same assumption we did before, which was that the acceleration is equal to 0, I can say the summation forces in the x direction equals mass times acceleration in the x direction. Using the acceleration equals 0, I get mg minus t is equal to 0. And this gives me equation 3, which is that t is equal to mg. Okay. Now I can combine equations 1, 2, and 3. And in doing so, what I'm going to get is mg minus the static friction force. And of course, the static friction force is going to be the normal force. If I want the bare minimum force or the bare minimum mass, or the maximum mass, I should say, that can hold it, then I got to consider the friction force that's maximal. So I'm going to say 0.40 times 78.27 newtons. That's the static friction force. And now I'm going to say minus 58.97 newtons. And that looks like all the forces we've had. I've obviously used equation 3 by replacing T with mg. I used equation 2 by having this whole function here equal to 0. And I've used equation 1 by using the normal forces equal to 78.27. So now I can go ahead and solve for M. So solving for M, I get M is equal to, now the 0.4 times 78.27 is 31.31 if memory serves me. So the 0.4 times 78.27 is 31.31. When that comes to the other side, it's going to be positive. So it'll be 31.31 newtons. Now, of course, that's 2 sig figs times 2 sig figs. So the 3 and the 1 after the decimal are not significant figures. So I put that there. And also when the 58.97 comes over to the other side, it's also going to be positive. So I'll say 58.97 newtons in that case. So that's got everything but the mg on the right hand side. And now I've got to divide by g, which is 9.80 meters per second every second. And that'll allow me to find out what M max is. So M max is done by getting that math. Now, one thing I got to do is because I'm adding here, remember that has the weird sig fig problem. When you add or subtract, you have to round the answer to the least number of decimal places that the either answer had. So when I add 31.31 and 58.97, the number has to be rounded to the ones place. If that addition or subtraction had come down to just a single digit to the left of the decimal, then I only have one sig fig. If it come up to like 100, then I had 3 sig figs. In this case, it came up to 90.28. So I have 2 sig figs. This is 90.28 newtons over 9.80 meters per second. And that gives me 9.212. And that mass, or that unit, is kilograms. And of course, these last 2 sig figs are not useful. So the answer for M max is 9.2 kilograms. So the maximum it can be is 9.2 kilograms. If it's any bigger than that, it's actually going to cause it to go up the incline. Now, all I have to do is look for M min. So here I'm going to say, look, or let's say, looking for M min. Okay, the difference between looking for M min and looking for M max is, in the case of M min, then the tension's still going to pull up the incline, but the friction force is also going to act up the incline because both the hanging mass and the friction are trying to keep it from going down the incline. So what I get is equation 1 stays exactly the same. So I'll say 1, the normal force is equal to 78.27 newtons. And of course, the 2 and the 7 are not sig figs. Equation 2 is going to be a little different. Specifically, it's going to have T. In this case, it's going to be plus Fs. So I'm going to say plus 0.40. Notice I'm still using static friction because we're assuming it's not moving, and I just did something really bad looking here. So let's fix that up. So 0.40 times 78.27. Whoa, I made that really small. Sorry about that, guys. Times 78.27 newtons. Again, those are not there. Notice I've changed the sign on it. It was T minus the friction force. Now it's T plus the friction force. And then it's minus 58.97 newtons. And all that's equal to 0. So that's what changed there. And then, of course, equation 3 was T equals mg, and that didn't change either. So 3T is equal to mg. So I can combine 1, 2, and 3, just like I did before. And this time I'm going to get M min is equal to, what we're going to see here is 58.97 is going to go to the opposite side because I'm actually plugging in mg for T. So it's going to be positive 58.97 newtons. And then that's going to be minus 31.31 newtons. And then all that will be divided by 9.80 meters per second. And that's going to give, again, because I'm doing subtraction, I got to do 58.97 minus 31.31. That gives me 27.26. So I know rounding it to the ones place gives me 2 sig figs. So that's 27.66, which I'm going to divide by 9.8. and that gives me 2.822 kilograms again, but that's 2 extra sig figs. So in fact, M min is equal to 2.8 kilograms. So the range really is from 2.8 kilograms, meaning if it's smaller than 2.8, then it's going to slide down the incline. If it's bigger than 9.2, then it's going to slide up the incline. Now that brings us to part B, which is what if M is 10 kilograms? So for part B, we're going to proceed as follows. Anybody have any questions on this? Okay. M equals 10.0 kilograms implies T is equal to 98.0 newtons, which means that the block is going to slide up the incline. Now, the reason I'm doing that is I got to see, is that force really big enough to overcome the static friction force? We found that the static friction force is 31.31 newtons. It's clearly bigger than that. And also there's another force of 58.97. So if I do 58.97 plus 31.31, I get 90.28. So 58.97 plus 31.31 newtons is equal to, as I said, 90.28, which is greater than mu static equals 31, or excuse me, mu static equals, oops, I shouldn't have done it that way. Yeah, because the static friction is the only one we're trying to deal with, and I was adding it like twice there. So let me kill that real quick. So we got all that. Okay. So now I can see that, in fact, and let me just fix this. That's driving me crazy. So now that I can see, I can look back at equation 2 in the first form, which was T minus Fs minus 58.97. Really all I have is the 98 minus Fs minus 58.97. That dictates whether it moves. So actually, yeah, I am supposed to compare that to 31.31 and 58.97. So 98.0 newtons is greater than 58.97 newtons plus 31.31 newtons, which equals, of course, 90.28. So that's really what I was trying to say. So that means F goes to F kinetic, meaning it's exceeded the static friction, which is what this was. So the friction is going to be kinetic, and that gives us now equation 2 is going to become 98.0 newtons minus the kinetic friction, which we found the kinetic friction was, actually we didn't do that at all with this one. The kinetic friction is supposed to be 78.27 times 0.3. So 0.30 times 78.27 newtons minus 58.97 newtons. All that's got to be equal to 10.0 kilograms times A. That's what equation 2 is. Now the tension is a little different. So equation 3 is now going to become, if you look at it, it was supposed to be mg minus t equals 0, but now it's mg, which is 98.0 newtons, minus t is equal to 10.0 kilograms times A. And those two A's are identical, right? The string can't get slack and the string's not going to stretch. So they're supposed to be identical. We should be good to go on this. I can solve this for t, and what I'll see is t is equal to 98.0 newtons minus 10.0 kilograms times A. So I'm going to call this equation 3 prime, and I'm going to plug 3 prime into, I'll say that 2 was actually 2 prime. So I'm going to say plug 3 prime into 2 prime. And when I do that, what I'm going to get is 98.0 newtons. That's bothering me. I don't remember having 298.0 newtons. Let me double check and see if I didn't do that already. Oh, that's what I did. Okay, so let's correct this real quick, everybody. The problem here is that this 98 is not supposed to be there. Because that's going on the assumption that the friction, or excuse me, that the tension is 98. So that's not supposed to be there. So let's erase that and just call it T. Everybody catch that on their notes? Sorry about that. I didn't make this mistake earlier. That's aggravating. So what I'm going to do is just say T minus the static friction force minus the mg sine theta is equal to 10 kilograms times A. And then equation 3 prime, or 3, is right. So we're good to go on that. Now I'm going to plug the 3 prime into 2 prime, and that T is going to be replaced with 98.0 newtons minus 10.0 kilograms times A. Then I have the minus. Now 0.3 times 78.27 gives me 23.48. So that's going to be 23.48 newtons. I'm going to go ahead and let you guys know where that came from by doing this and say this is 23.48 newtons. Of course, you only had 2 sig figs, so those are not supposed to be there. And then I'm going to say the rest of equation 2 prime is minus 58.97 newtons. And that's equal to 10.0 kilograms times A. So I can get the 10 kilograms on the right-hand side. That's going to become 20.0 kilograms times A. And then all I got to do is the rest of the math, which is 98 minus 23.48 minus 58.97. And that gives me 15.55 newtons. Now notice the 98 was good to 1 decimal place, but the 23.48 and the 58.97 were only good to the ones place. So that means the 55 there after the decimal is not significant. So now I can say that A is equal to 15.55 newtons divided by 20.0 kilograms. And that gives me 0.77 0.75 meters per second every second for the acceleration. And I really am only supposed to have 2 sig figs, so I should underline that. So now I have that A is equal to 0.78 meters per second every second. And that's how you solve that problem. Anybody have any questions on that one? Sorry about that, inadvertently plugging in the 98 for T prematurely. No questions? All right. So it looks like we don't seem to have any questions. So I'm going to go ahead and do the last part that I really wanted to make sure you guys understood. And this is an application of the centripetal acceleration. So I'm going to actually design a curve at an angle, at a steep angle theta, so that for a given velocity v, a vehicle of mass m can take a turn of radius r. And I'm going to use that to decide what angle theta is the right angle. And then I'm going to calculate it for a very specific angle and a very specific radius of the turn. So that's just a typical application of mv squared over r, or v squared over r being the centripetal acceleration. I'll tell you, your book's got some good examples. One that I definitely recommend you doing is, if you've ever been to the beach, you've probably, or a pool or anything else, you've probably taken a bucket at some point, filled it up with water, and spun it so fast that the water didn't spin out. That's a wonderful problem to work. You can basically realize that the force of gravity, when the bucket's upside down, the force of gravity can either be, if it's not going too fast, the force of gravity can actually be the force required to keep the bucket going in a circle, or it could be greater than the force required to keep the bucket in the circle. And in both cases, the water will not spill out. And then when you get at the bottom, of course, it's going to be a lot heavier. But that's one problem you can work out to figure out how fast it must go to keep from spilling out. Another one is, if you're actually on the equator of the Earth is rotating. And if you actually stood on a scale, it wouldn't read mg, because mg would be what your weight was, let's say if you're on the North Pole. But because you're on the Earth and the Earth is rotating, the rotation of the Earth means that you have to go in a circular path, and part of your mg is being used to accelerate you, being used to accelerate you in the direction towards the center of the Earth. Therefore, your weight is going to be, your apparent weight is going to be mg minus that mv squared over r. So that's another really good problem to work. And you can do that for different latitudes. Of course, at the latitude of 0, which is the equator, then the radius is the full radius of the Earth, and the speed is basically whatever speed the Earth would have to have for it to turn one circumference in 28. It's technically about, I mean, you could call it 24 hours, but it's really about 23 hours, 56 minutes, because there's a difference between a sidereal day and a solar day. But that's not really a huge difference. So just call it 24 hours and that'll be done. So anyways, those are all good problems. I've done some like that before on my YouTube channel. You can find some in your book as well. You can find other ones at Khan Academy, all sorts of good stuff. But I'm going to go ahead and do this banked curve problem. So let's start off with imagining a banked curve with a car riding on it. So what I'm going to do is I'm going to draw a banked curve. Okay. And that banked curve, whoa. Oops, did not mean to do that. That banked curve is supposed to be at an angle theta. And that's the angle that we want to know. And in fact, it has a car driving on it. And the car has a mass m, and it's moving at a velocity v, and the radius of the turn is going to be r. So we're pretending like we know m, v, and r, and we're trying to solve for theta. Okay. So I'm going to draw a free body diagram, but when I draw this free body diagram, I'm not going to tilt the axes. It turns out this is much better with the axes not tilted. You can still, of course, tilt them if you wanted to, but it turns out the problem's a lot easier to solve if you don't do that. So I'm going to make this my y-axis. I'm going to make this my x-axis, and then I'm going to draw a inclined plane like this, and that's supposed to be at an angle theta. I've obviously drawn it a bit big, but that's okay. It's not too horrible. Now, because of that, I'm going to have a normal force that's perpendicular to that. So there's my normal force. Notice I'm using blue because it doesn't align with either the x or the y axis. So the forces acting on this car, which has a mass m, are in fact in the negative direction. We're going to use again the red vector. So I have here a force of mg. Now, if we look at the triangle formed by the inclined plane, I think you can see that this angle right here is 90 minus theta. And because of that, this angle right here must be theta. So we can now, for instance, use that to help us because that's a vertical angle with this angle, which means this angle right here is theta. So now I can draw a positive vector component in the y direction. And actually, let me make this a little shorter because I made it so big I can't really fit it in. So I would, ooh. So I'll do like that. That looks good enough to me. Okay, so I have a vertical x component or y component. That's what I call in the positive y direction. And that's this force right here. And I've also got a right pointing x component, and that's also in the positive direction. So it's going to be right here. This one I think you can make out is Fn times the sine of theta. And this one right here is Fn times the cosine of theta. Everybody follow that? Now I'm going to design this curve where it doesn't require friction at all. So I'm saying at what angle theta will no friction be required for a car of mass m traveling at v in a curve of radius r. So by stating it that way, it lets you know that we know m, v, and r, and we're asked to solve for it. So there's no friction forces here. I'm just going to, in fact, solve the problem using Newton's laws of motion. And Newton's laws of motion that are relevant to us is the summation of the forces is equal to mass times acceleration. And I'm first going to draw the y motion. And I'm going to say the equation for the y motion is the summation of the forces in the y direction equals mass times acceleration in the y direction. And I don't want any of that acceleration in that direction. So I'm just going to say 0. And what I end up getting is that Fn cosine theta minus mg is equal to 0, which tells me that Fn is equal to mg over cosine theta. Now, that's not the normal way we do it, but we normally use a tilted coordinate system, so we shouldn't expect it to be the same. In fact, this is correct, and it's going to work out nicely, as you'll see. Now I'm going to do the summation of forces in the x direction. Anybody have any questions on anything I've done so far? We've got about 5 minutes left, so we've got plenty of time. All right, well, let me do the summation of forces. So the summation of the forces in the x direction equals mass times acceleration in the x direction. In this case, you got to remember that, in fact, for you to go in a circle, you actually have to have an acceleration. That acceleration has to be your centripetal acceleration, which we derived last time. So there's literally only one force pointing in the x direction, and that's Fn sine theta. So we get Fn times the sine of theta is equal to m times v squared over r, because v squared over the r is the centripetal acceleration. That's going to be equation 2. So what I'm going to do now is plug equation 1 into 2. And when I do that, I'm going to get basically mg over cosine theta times the sine of theta is equal to mv squared over r. You can see that the m's cancel out, which is great, because we wouldn't want to have a universe or a world where the mass of the car dictates what the incline of the banked curve should be. And we'd have to have, of course, different banked curves for Volkswagen Beetles and Honda Prius or whatever than we do for Mack trucks. So that's kind of nice. We can also notice that sine over cosine is tangent. So the ultimate result that we get is that tangent theta is actually equal to v squared over g times r. Or alternatively, you could say theta is equal to the tangent inverse of v squared over gr, like that. Both of those are perfectly acceptable. And now what I want to do is consider one specific case. Let's specifically consider 60 miles per hour with 100 radius turns. So what is theta if v equals 60 mph and r equals 100 meters? That's a pretty good turn radius, by the way. Okay. We can actually make this a little easier on ourselves. I'm just going to Google 60 miles per hour is 26.82 meters per second. So this is 26.82 meters per second. That makes life a little easier. I don't have to do that work, and we're all good. So theta is in fact going to be equal to the inverse tangent of 26.82 meters per second squared divided by 9.80 meters per second every second. And that's the G. And then the 100 meters, notice that makes meters squared per second squared under meters squared per second squared. So I'll get 26.82 squared divided by parentheses 9.8 times 100, close parentheses. That gives me the inverse tangent of 0.73399. So now I'm going to take the inverse tangent of that. And that gives me 36.3 degrees. Or 36.28 degrees. So there is a specific example for you in case you wanted that. Any questions on that?
I have a question.
Yes.
So why is f sub n sine theta equal to mv squared over r? Like, where does the mv squared over r come from? I know where it comes from, but like, why is it?
Okay.
There?
So last time I did a derivation where we found out that r of t could be represented by r times the sine of 2 pi over capital T times t I hat plus r times cosine 2 pi over capital T times t j hat. That was the trajectory or the orbital equation, if you will, for a particle going in a circle at a constant speed. And when we did the calculation, we found out that the magnitude of the acceleration that had to be that had to exist for it to make that circle at constant speed was v squared over r. So we just worked it out where v turned out to be 2 pi r over capital T, where t was the time required to make one complete revolution. So doing that, we were able to figure out that the acceleration's magnitude had to be v squared over r. That's where the v squared over r came from. The right-hand side of Newton's law says mass times acceleration. Since we wanted to go in a circle, the acceleration had to be that v squared over r. So hence we got mv squared over r. Does that make sense?
I understand the centripetal force aspect. I just don't know why it equals, like, why does it equal f sub n sine theta?
Okay, so if you look at the free body diagram I have drawn there with the green arrows, notice the only forces pointing in the x direction at all is Fn sine theta. And we didn't have any freedom in that. We had a normal force, and the definition of a normal force is that it's perpendicular to the road surface. So the road surface was pitched at an angle theta. That meant the normal force was pitched at an angle theta from the y-axis. And therefore, the component of it in the x direction was Fn sine theta, and the component of it in the y direction was Fn cosine theta. So literally, that was the only force. It was basically the component of the normal force in the x direction is the thing that's providing the centripetal acceleration. That's
I get it now.
Does that make sense?
I get it. Yes, because we're saying that equal to mv squared over r to see like what. Yeah, that makes sense to see the angle.
Gotcha. Good question. Now that's exactly the kind of thinking you need to do. Is where did that come from? And that's what you have to do when you're reading the books as well. Is you gotta try to make sense of every equation they write and figure out why did they write it that way. And if you can't, then that's a good time to ask me or to Google it or ask another student. But definitely get the answer. Normally I should be able to answer it for you though. Okay. All right, we're done. You guys are free to go. I will wait for the last person to leave. There was one person that said they missed a test. I'm not going to be mean and take points off for you missing it, but I will open it back up. But I need to know who that student is. So I asked them to make sure they didn't split. So if you could do that, that'd be great. I'm going to go ahead and kill this sharing screen unless someone tells me, is anyone trying to copy that? So we got more than one person that missed the test. Okay, I'm going to stop share.
I also missed the test.
Okay, so I have Sean that missed the test, and who else did I have? Josh. Okay, and was there a third person, or is it just those two? All right, no problem. Normally, of course, that's a real bad thing to miss tests. So guys, please pay attention. If you first log in to the Canvas system before you choose a particular course, there will be things over in the right-hand side that says stuff that's available. So if you guys take the time to check Canvas like once a day, that'll keep you from missing those. So just in the future, I'm not trying to, batter you or anything. I just wanted to make sure you don't miss any more. So I'm going to the modules now in our course, and I'm going to open test 2 back up, and that's test 2, chapters 3 and 4. And that was last available September 26th. Actually, no, I never did that with that. Okay. One of the tests I shared the correct answers with. If I had done that with this one, I'd need to make you up another one. So I don't have to do that with this one because I never shared the correct answers. So I'm now going to make this test. Let's say you guys have until 11:59 p.m. on October 1 to finish it. I would highly recommend you do it before that, just because there's a good chance you might forget, but it's now available until 11:59 p.m. October 1. So good luck. I hope you kick butt, get a good grade, and you guys have a good, safe weekend. Holler if you need anything. I will be here, and good night.
Oh wait, excuse me, Professor.
Yes.
Sorry. I was trying to wait till you were done with them.
Oh, no problem.
And one of the students that I had emailed you earlier this semester about me getting dropped from the classes due to an issue with financial aid.
Yeah, I remember that.
Yes, so and I remember I did a quiz before I was dropped. I think it was like one of the first ones.
Okay.
But I see that there are some assignments that I don't have a grade for, or it says missing, and I'm trying to play catch up from that happening. I missed some dates, and I was trying to see if the possibility I could like do something.
Let me see what's going on here. I'm trying to see what, if anything, you missed.
I did look at
marks wouldn't
this
be
and said
damaged.
to drop.
Right. Yeah, it's actually showing currently like you've done oh, okay, so I do have your test 1 and test 2. So that's good. Your test 3 I have as well. So you really haven't missed anything but your homeworks.
Homeworks, okay.
Yeah, I'm looking at it. Everything looks okay. I will remind you that the practice tests are completely optional, but one, they are your best tool for preparing for the actual test. And 2, at the end of the semester, I take each of your highest practice test grades. There's one for every test. So I take each of those and take the highest score. I average them, divide that score that could be as high as 100 by 20. And then that many points are added to your final course grade. So you really, really, really don't want to not do them.
Yeah.
Because you're just giving away a potential 5 points. But other than that, you haven't missed anything. So other than, like I said, the homeworks through my lab and mastering.
Am I able to still do those, or
yes, I think it gives you more or less the whole semester, but what it does is it takes off a certain amount of points per day up to some maximum number of points. So if you just do them and let me know as you get them done, like each time you get, 1 or 2 done, send me an email or a text message would be even better, and say, hey, this is, give me your first and last name and tell me exactly which ones you did. Then I can go in and correct that for you. Okay. I'll let you, because you had those problems, I'll let you make up, let's say 2 of them. And the other ones, you'll just get some points off, but I'll give you 2 of those made up with no points off for being late.
Thank you. I appreciate that.
Actually, it should be 4 because it's 2 homeworks per chapter. So 4 for 2 weeks, in other words. Okay.
Okay. Thank you.
You're welcome. Have a good one, Melissa.
All right. You have a good day.
All right, so speaking of homework,
Yes.
this is John. I have
Okay.
caught up to chapter 3, and I'm gonna be starting on chapter 4 tonight. I just wanted to give you a heads up. That's where I'm at.
No problem.
I do have a question on the test.
Hold on. Let me stop recording this.
Yep.
Okay.